Hey everyone, welcome back to Math 261. This is Scott. Let's get started. So what we're going to talk about right now is section 1.5, in which we're going to explore a little bit more the solution sets of linear systems. Now, by linear systems, what we mean is any of the equivalent situations that we've looked at so far that match a system of linear equations. So linear system can mean either a matrix equation, a vector equation, or a system of linear equations, as those are all different sides of the same fundamental phenomenon. So first off, what we're going to do is we're going to look at a more specific, narrow case to begin with, and then we're going to see how that connects to the more general case. So first, we're going to look at what are called homogeneous systems of linear equations, or just homogeneous systems. Homogeneous systems. So what makes a homogeneous system homogeneous is that the constant terms are all zero. So these are systems of linear equations whose constant terms are all zero. So for example, it could be something like this, where we have 2x1 minus 3x2 plus 4x3 equals 0. And then maybe we have 5x1, and then maybe we don't have an x2 term in this particular one, and then it's plus just x3 equals 0. And then maybe what we have is something like 5x1 minus 2x2 plus 3x3, and again equals 0. These all have to be zeros. All zero in homogeneous systems. So they're all zero in homogeneous systems. All right, well then in matrix form, what that would look like is this. Ax equals the zero vector. So we would have some system of coefficients that would represent these numbers over here, all equaling just the zero vector. Now for any of these systems, any of these homogeneous systems, there is always one particular solution that is on offer, and that's what's called the trivial solution. So note, if x just equals the zero vector, this is always a solution to a homogeneous system. So this is always a solution to, say, a homogeneous system. This is called the trivial solution. And it's called the trivial solution because it is trivially true that if you were to take 2 times 0 minus 3 times 0 plus 4 times 0, you will sure enough get 0. If you do 5 times 0 plus 0, you will sure enough get 0, and so on. Where there are no constant terms, zeros all around are just going to produce a 0. So this is called the trivial solution. Every homogeneous system has one. It's not very interesting, and that's why it's called that. Now, as for non-trivial solutions, that's a little bit more. Let's get a little bit more meat on its bones. So, non-trivial solutions. So non-trivial solutions. So these are where x does not just equal the 0 vector; it equals something else. Now this is more interesting, hence the name. So now, what would it take for there even to be such a thing as a non-trivial solution? Well, if you think about how this would all shake out, if suppose we were deep in the weeds of this particular problem and we were trying to actually solve this, we would go about it by row reducing, and then as long as we just were able to say x1 equals something, x2 equals something, x3 equals something, and these were all just numbers, then we would end up being able to definitively say there was a unique solution. But what numbers would they be? They would be 0, 0, and 0. So if there's a unique solution, it's the trivial solution. So in order for there to be a non-trivial solution, there must be more than just one unique solution, which means we must have free variables. So ax equals 0 has non-trivial solutions if and only if there are free variables. So if there are no free variables, if you end up with all basic variables, then you will only have one unique solution. And if there's only one unique solution, and we know the trivial solution is always on offer, then it must be that one. So now let's try to actually figure out a way to write the solution set to particularly first homogeneous systems of equations and then just general systems of equations. So writing solution sets in parametric vector form. So first off, just talking about the homogeneous systems first. Well, actually, the same description will work for both. We'll just show it first with a homogeneous system, and then we'll bootstrap our way up to non-homogeneous systems. So the idea here is what we will first do is we will do the row reduction. That is going to be our first step in a lot of these situations. So the idea is first row reduce. In particular, row reduce as much as you can. So say into reduced row echelon form or reduced echelon form. First row reduce into reduced row echelon form or reduced echelon form. Then solve for each basic variable in terms of the free variables. in terms of the free variables. Then, after that, then state a generic vector based on the above expression. Pull out the free variable to treat as a parameter. Pull out the free variables to use as parameters. Now this is a little bit hard to see what's going on here. It's a little bit neither here nor there in just terms of like generic vector and so on. So let's actually try this and see if we can make sense of it or not. That's always the way to tell if something makes sense, is to actually put it into practice and see if we can get it to work for us rather than being a hassle for us. So as an example, let's take the system with, so we're just going to cut to the chase here. We're going to skip straight to the augmented matrix. System with augmented matrix, and let's say it looks like this: 1, 0, 2, 0, 0, 1, 3, 0, 0, 0, 0, 0. So here we're assuming that it's actually already in our REF form. So whatever the augmented matrix was, we actually already did the row reduction. So let's just go ahead and say it in our REF. So let's say we had some coefficients, we did the row reduction, we ended up with this. Now it's in reduced echelon form, but we have our pivots here, and then a free variable here. So this is going to be the column that goes with x1, this is going to be the column that goes with x2, this is going to be the column that goes with x3. This one is the pivot, the augmentation bar, and then over here we're just going to have the b's. And you'll notice this one does happen to be homogeneous, which is nice. So then what we're going to do is we're going to express each of the basic variables in terms of the free variables. So first, just taking off the first line here and writing it in the equation form. We're going to have x1 plus 2x3 equals 0, which is then going to lead us to the conclusion that x1 is equal to negative 2x3. So be it. Now the next equation here is going to take us to x2 plus 3x3 equals 0, which is going to lead us to the conclusion that x2 is equal to negative 3x3. Now as for the free variables, the easiest, most consistent thing to do for those, actually so it's not even a matter of rewriting this equation, the most convenient thing for dealing with those is just to write them also in terms of themselves, and I'll show you what I mean by that. So then x1 is equal to negative 2x3, x2 is equal to negative 3x3, and then the free variable x3 just equals itself. So this is how we'll treat the free variables. So do this. for free variables. And then if we think about what we would have for a generic element of the solution set here, that would be a generic vector x, which is equal to x1, x2, x3. But wait, what did we say x1, x2, and x3 were each equal to in terms of x3, the free variable? That would be negative 2, x3, negative 3, x3, and then just x3. And that's what we mean by stating a generic vector based on the above expression. So x1, x2, x3 are all like this, and then we're going to pull out the free variable to use as the free variables to use as parameters. Here there's only the one free variable, it's x3, so I'll pull that out to the front. It will be the parameter here, and we'll have x3 times negative 2, negative 3, and then 1. So this is a parametric vector form that would be expressing the solution set for x. Parametric vector form. Now, what if what we had was a non-homogeneous system of equations? So let's take that as an example. So this is an example where it's non-homogeneous. We don't have to change our procedure at all. We can just watch how it all plays out. So as an example, let's say that we have something like this. So this is again the augmented RREF matrix. So we can just cut to the chase. We can cut out all the legwork that we would have to do perhaps in the wild originally. And let's say what we had was something like this. We had 1, 0, 3, so just like before. Then negative 1. Then 0, 1, 1. I'm sorry, not quite, just like before. It's got slight differences here. Negative 2. And then let's say 0, 0, 0, and 0. So once again here, this represents x1, this represents x2, this represents x3, this represents the line of equal signs, and so this is the augmentation column here, and this represents the b. Okay, so then if we translate this, we're going to have x1 plus 3x3 equals negative 1, which then we can solve for the basic variable in terms of the free variable. So it's going to be negative 3x3 minus 1. So make a note of that. And then we're going to have x2 plus x3 equals negative 2, which is going to then lead us to the conclusion that x2 is equal to negative 2, sorry, I should say negative x3 minus 2. And then as for x3, that just equals itself. That's what we'll do to all of our free variables. Okay, well then what's that mean? x1 is equal to negative 3x3 minus 1, x2 is equal to negative x3 minus 2, x3 equals itself. And so then that means the generic elements of the solution set here are going to be x1, x2, x3. Which in this case will specifically give us negative 3x3 minus 1, negative x3 minus 2, and then just x3. which we can then separate out into two pieces, the part that has x3's and the part that doesn't. It's going to be negative 3x3, negative x3. I should say up here. We should say for this example, this is an example of a non-homogeneous. And then x3 and then plus negative 1, negative 2, and then 0 for there. We need to have something in that, and it is 0. And then we can pull out the x3 from this part. This is x equals this, x equals this, x equals x3 times negative 3, negative 1, 1. So just peeling the x3 away from its coefficients there, plus negative 1, negative 2, and 0. Now, the way this shook out is actually going to be the same as the way you can shake it out in all non-homogeneous cases. And what this basically means is that you can always separate it out into a solution, the generic solution to the associated homogeneous system, plus one particular solution to a non-homogeneous system. So this is a note. It's not actually something that is going to be very relevant to us. However, those of you who are going on into Math 256, this is actually one of the very fundamental notions of solution sets to differential equations, and it has to do with the fact that there's a certain parallelism between linear systems and differential equations, and it has to do with this. So note for non-homogeneous systems, let's say for a non-homogeneous system, with a particular solution P, any other solution will have the form W equals, so that P, which is a particular solution, plus VH, where VH here represents a vector that is a solution to the homogeneous equation. So this is the particular non-homogeneous solution. And then here, this one represents a solution to the associated homogeneous system. So again, this is a fact that is not actually going to pay off in this class, but its payoff is going to come, in fact, in the next class. So the next class is going to which is Math 256, is going to be where this really gets its payoff. So this is very important. For Math 256, more so than it is for us. Geometrically, what this means is that the solution set to a system of equations forms what is called a hyperplane. However, that's not something that is quite within your pay grade right now, so we're not going to write it down or anything. I just want to let you know what it generally means. So a hyperplane is you take a plane through the origin and you shift the whole plane by a certain amount up, down, left, right, so on. So you have a plane. If it's 2 dimensions, it looks like a sheet. If it's 1 dimension, it looks like a line. If it's 3 dimensions, it looks like space. If it's 4 dimensions, we don't know what it looks like because our brains aren't wired that way. But the solution to a homogeneous system is just a plane that goes through the origin. Now, and by the way, the number of free variables determine how many dimensions there are. So if it's a 2-dimensional plane, that means there are 2 free variables. Now, what this means is if it's non-homogeneous, you can just think of that plane being shifted off of the origin a little bit. And that shift is the vector p. P is essentially the displacement vector by which the whole plane has been shifted off of the origin. Now, that's something that will make a little bit more sense as the term progresses. But for now, just let it suffice that it has a geometric meaning. That geometric meaning is a shifted plane, which is what is called a hyperplane. The number of dimensions on the solution set corresponds with the number of free variables. But for us, what we need going forward here in order to be able to make use of this is actually just this procedure that we used right above here to get ourselves the parametric vector form of the solution set to the system of equations, whether homogeneous or not homogeneous. Alright, so that's going to basically do it for section 1.5 for us in this episode of Math 261. I'll see you next time for a little bit more linear algebra action. Till then, bye.